Okay, so hold on, welcome back. So we have basically reached to this point where we can talk about the transpose of a matrix. And so what we have here says that in this section we shall learn about transpose of a matrix and special types of matrices such as symmetric and skew symmetric matrices. So as a definition, we have definition number 3. We have basically if A as a matrix A of ij be an m by n matrix, then the matrix obtained by interchanging the rows and columns of A is called the transpose of A. Then the matrix obtained by interchanging the rows and columns of A, by interchanging the rows and columns of A is called the transpose of A. Is called the transpose of A. The transpose of A. Transpose of the matrix A is denoted by A prime or A transpose. Transpose of A is denoted by A prime or A transpose. In other words, if you can say that if A is a matrix of Aij with the order m by n, then A prime is equal to a matrix of Aj with the order n by n. M by n, n by m, ij, ji, right? For example, as an example, so you have, for example, A is this matrix here, 3, 5, and square root of 3, 1, and 0 and negative 1/5, and I need to write things a little bit more neatly. So that is A. Then A prime would be basically the same matrix, but this column, the first column becomes the first row, the second column becomes the second row. So we would write this as 3 square root of 3, 0, for example, and 5, 1, negative 1/5. And that would be A prime. And here you have a 3 by 2 matrix. Here you have a 2 by 3 matrix. So that's basically the whole story. Now you can of course use this concept in many different ways, because it's a standard part of matrix algebra, or basically the whole body of matrices. And if you happen to be able to use it when you're doing something in mathematics, or when you're doing something using mathematics, then of course this is something that you can use. Now the properties of of matrix of transport of the transpose of the matrices, the properties of the transpose of the matrices. Now there is a couple of properties of these of the transpose of matrices that we can talk about. So there is the following properties of transpose of matrices, and these have been stated here without proof, and these may be verified by taking suitable examples. I think the proof for these would have made the text much larger, or it would have required a little bit of higher mathematics in order to prove these, so they have not provided the proofs here. Okay, so now about the properties of the transpose of the matrices. So we have, for any matrices A and B, for any matrices A and B of suitable orders, we have basically the transpose of A, or A prime prime basically is equal to A. And number two, you have Ka transpose, Ka whole transpose, meaning that you take a scalar multiplied by a matrix and then take the transpose of that matrix, is the same thing as basically Ka transpose, where K is any where K is any constant. Right? Now, and of course, number three, A plus B whole transpose. A plus B whole transpose is equal to A transpose plus B transpose. Or A times B, number four. This is a little bit different. So AB whole transpose is equal to B transpose times A transpose. So that's basically the four properties of the transpose of matrices A and B. So now let's do a couple of examples. Now example 20. Example 20, we have if A is equal to some matrix, like for example 3 square root of 3 and 2 and 4 to 0, and B is equal to some matrix like 2, negative 1 and 2, 1, 2 and 4. You want to verify that number one, A transpose whole transpose is equal to A, and number two is A plus B whole transpose is equal to A transpose plus B transpose, and number three is K times B whole transpose is equal to K B transpose, where K is just a constant, right? So now basically number one, we have basically to show that A transpose whole transpose is equal to A, we have, so you want to take A A is equal to this matrix 3 square root of 3, 2, 4, 2, and 0. Take the transpose of that. So A transpose is equal to basically taking, for example, this row and make a column out of it. For example, 3 square root of 3 and 2 and 4, 2, 0. And again, take this matrix and take the transpose of that, which is A transpose whole transpose is equal to, take for example this column and make a row out of it, 3 square root of 3 and 2 and 4, 2, 0. And you can see that this is actually equal to A. And therefore, A is equal to A transpose whole transpose. Now, part B of this question, part 2 of this question, part 2, to show that basically A plus B whole transpose is equal to A transpose plus B transpose. We have basically, let's take A plus B and see what we get there. So A is equal to, or to calculate A plus B, we have basically 3 square root of 3 and 2, 4, 2, and 0, plus B, which is equal to 2, negative 1, 2, 1, 2, and 4. And then if I add these together, I get 3 plus 2 is equal to 5, square root of 3 minus 1, 2 plus 2 is equal to 4, 4 plus 1 is equal to 5, 2 plus 2 is equal to 4, and I have a 4 over here. Now A plus B whole transpose is going to be equal to 5 square root of 3 minus 1 and 4 and 5, 4, 4. That is going to be A plus B whole transpose. Now if I take A transpose, if I calculate A transpose, this matrix is A. This one is A, this is B. So A transpose is going to be equal to the transpose of this matrix, which is 3 square root of 3, 2 and 4, 2, 4, 2, 0. That is A transpose, and B transpose is the same thing as basically 2, negative 1, 2 and 1, 2, 4. And now A transpose plus B transpose, A transpose plus B transpose is equal to 3, 4 square root of 3, 2, 2, 0, and that added to 2, 1, negative 1, 2, 2, 4, which is equal to 3 plus 2 is equal to 5, 4 plus 1 is equal to 5, square root of 3 minus 1, 4, 4, and 0 plus 4 is equal to 4, which is actually equal to this matrix here, which is the same thing as A plus B whole transpose, which means that A transpose plus B transpose is actually equal to A plus B whole transpose. That is the second part of this question. The third part of this question, is part 3 of this question. We have to show that basically Ka whole transpose is equal to Ka transpose. We have basically, what is A basically was a matrix like 3 square root of 3, 2 and 4, 2, 0, and therefore Ka is equal to, well, you can write it as K times, for example, 3 square root of 3, 2 and 4, 2, 0, which is equal to 3K square root of 3K, 2K, 4K, 2K, and 0. And if I take the transpose of this matrix, meaning that if I write K a whole transpose, that would give me the transpose of this matrix, which is 3k square root of 3k, 2k, 4k, and 2k, and 0. Now if I take the transpose of A, or A transpose, that gives me basically this matrix 3 square root of 32, 4 to 0, 4 to 0, and therefore K times A transpose is equal to K times this matrix 34 square root of 32 to 0, which is equal to 3k, 4k, square root of 3k, and 2k, and 2k, and 0. And if you take a look at these two matrices and compare them, you will see that they are the exact same matrices, meaning that this is actually the same thing as Ka whole transpose, which means that Ka transpose is equal to Ka whole transpose. That is basically the three parts of this question. Actually, the third part was, the question was a little bit different, meaning that I was supposed to show that K B basically whole transpose is the same thing as K B transpose, but that's basically the same story, meaning that you would do it in the exact same way. So as another example, we can mention, for example, example 21, which is A is a matrix as -2, 4, and 5. It's a column matrix. And B is a matrix of 1, 3, and -6. Okay, so basically you have these two matrices, and you want to verify that basically AB whole prime is the same thing as B prime times A prime. So to calculate basically, for example, your LHS, you have A times B is equal to -2, 4, 5 times 1, 3, and -6. This is a 3 by 1 matrix, and this is a 1 by 3 matrix. So you get a 3 by 3 matrix. So you have basically -2, -6, you have +12, you have 4, 12, and -20, 4, 12, and -24, you have 5, 15, you have 5, 15, and -30. That is A times B. Now to calculate AB whole transpose, you will take all of these basic, for example, all of the rows and make columns out of them, meaning that you have -2, -6, and 12, 4, 12, -24, and 5, 15, -30. That is AB whole transpose. Now, B transpose is the same thing as 1, 3, and -6. A transpose is the same thing as -2, 4, 5. -2, 4, and 5. Now B transpose A transpose is the same thing as 1, 3, -6, and -2, 4, and 5. And so you have a you have a 3 by 1 matrix and a 1 by 3 matrix, meaning that you get a 3 by 3 matrix. So -2, 4, and 5, -6, 12, and 15, and +12, -24, and -30. And if you compare these two matrices, you'll see that basically this is actually the same thing as AB whole transpose, which means that AB whole transpose is the same thing as B transpose A transpose. Right? Now the next thing that we have here is symmetric and skew symmetric matrices. Symmetric and skew symmetric matrices. As a definition 4, we have a square matrix. A square matrix A equal to A of ij is said to be symmetric. If A transpose is equal to A. That is A of ij is the same thing as AJI. For all possible values of I and j. Right, so it's simple, meaning that if you have a square matrix, take the transpose of that matrix. If you end up with the same matrix, then you call that matrix a symmetric matrix. As an example, if you have, for example, A is equal to square root of 3, 2, 3, 2, -1.5, -1, 3, -1, and 1. And here, if I calculate basically A transpose, I will get basically square root of 3, 2, 3 as a column, square root of 3, 2, 3 as a column, 2, -1.5, -1, and 3, -1, and 1. Right? And so as you can see, this is actually equal to A, meaning that A transpose is equal to A, and therefore A is a symmetric matrix. Now a skew symmetric matrix has a definition 5. A square matrix A equal to A of ij is said to be skew symmetric. If A transpose is equal to -A. That is A of ji. if I take A as A of ij, then A transpose becomes, of course, A of ji, and that is equal to negative A of ij, right? That is A of ji is equal to negative A of ij for all possible values of I and j. For all possible values of I and j. And so that is then a skew symmetric matrix, meaning that if you have a matrix A, take the transpose of that matrix, also take the negative of that matrix. If those two are the same matrices, then A is called a skew symmetric matrix. Now if we put I is equal to j, we have A of I is equal to negative A of I. So here we said that now if we put I is equal to j, we have, so over here we said that A of ji is equal to negative A of ij. So here we had this relationship between, we said that A of ji is equal to negative A of ij. If I is equal to j, then I can say A of I is equal to negative A of I. Or you can say that basically take this to the other side, A of I plus A of I is equal to 0, or 2 times A of I is equal to 0, or A of I is equal to, or A of I is equal to 0 for all i's. For all i's. That means that if I is equal to I, or if I is equal to j, that happens only when you have a square matrix, and for example you have these elements here, right? So you have all of these elements here, and over here I is equal to 1, j is equal to 1. Over here I is equal to 2, j is equal to 2. I is equal to 3, j is equal to 3. I is equal to 4, j is equal to 4. Meaning that across the diagonal of any square matrix, I is equal to j, right? Now here we are saying that for all i's, or you can say for all j's, A of I is equal to 0, meaning that across this diagonal all of these elements are equal to 0. And therefore we can say that this means that all the diagonal elements of a skew symmetric matrix are 0. For example, we have a matrix B which is 0EF, negative E, 0G, and negative F, for example, negative G and 0. Now, here if I take the transpose of this matrix, B transpose or B prime is going to be equal to 0EF, 0EF, negative E, 0G, and negative F, negative G, and 0, and negative B as well. If I calculate that, I will have 0, negative E, negative F, E, 0, negative G, F, G, 0. And you can see that these two matrices are actually the same matrices, meaning that this is actually equal to B prime. Therefore, B prime is equal to negative B, and therefore B is a skew symmetric matrix, right? So that is one example. Now what we are going to do is to prove some results of symmetric and skew symmetric matrices. So now we shall prove some of skew symmetric, prove some of results related to symmetric and skew symmetric matrices. So to begin with, we have a couple of theorems, actually only two theorems. So theorem number one, we have for any square matrix A with real number entries, for any square matrix A with real number entries, A plus A prime, which is the transpose of A, is a symmetric matrix, and A minus A prime is a skew symmetric matrix. So the proof for this theorem is as follows. Let B be equal to A plus A prime. Let B be equal to A plus A prime. Then B prime is going to be equal to A plus A prime whole prime. And well, we know that A plus A prime whole prime is equal to basically A prime plus A prime whole prime, because basically we said before that A plus B whole prime is equal to A prime plus B prime, right? Because of this, we can write this. And of course, this is the same thing as A prime plus A, because we said that A prime whole prime is equal to A, right? And also we know that we can write this as A plus A prime, because A plus B is equal to B plus A, meaning that matrix addition is commutative, right? So now A plus A prime, A plus A prime is equal to B. That is actually equal to B, which means that B prime is equal to B, and B is equal to A plus A prime. That means that okay, so now this proves that A plus A prime, and this proves that A plus A prime is a symmetric matrix, right? And the reason why it proves that is that basically here we are saying that for any square matrix with real number entries, meaning that A has real number entries and is a square matrix, and we want to prove that A plus A prime is a symmetric matrix. A symmetric matrix by definition is the kind of matrix in which the transpose of the matrix is equal to the matrix itself, meaning that, for example, if you have some matrix B, and if you take the transpose of that matrix as, call it, for example, B prime, if B is equal to B prime, then you can say that B is a symmetric matrix. Now what happens here is that here we are talking about A plus A prime as a matrix, and so we called it B basically. Now we take the transpose of that matrix, and the transpose becomes for all of this business that we have here, and we ended up with B. That means that B prime is equal to B. Since B prime is equal to B, then I can say that B is a symmetric matrix. And since B is the same thing as A plus A prime, that means that then A plus A prime is a symmetric matrix, right? Now, the next part of this theorem, so you can basically simply write here that B is equal to, therefore, for example, B is equal to A plus A prime is a symmetric matrix. It's a symmetric matrix, right? Okay, so now in order to prove that A minus A prime is a skew symmetric matrix, basically a skew symmetric matrix by definition, we said that if you have a square matrix A with, for example, A of ij, this matrix is said to be skew symmetric if A prime is equal to negative A, right? So that if that's the case, then you can call it a skew symmetric matrix. Now, what we need to do here is that we need to prove that for A minus A prime, basically the transpose of the matrix is equal to the negative of the matrix. So I take A as, for meaning that I can say, for example, let C be equal to basically A minus A prime, some matrix, for example. Now I can say that C prime, the transpose of this matrix, is equal to A minus A prime whole prime. And previously we said that A plus A prime, or A plus B, we said that A plus B whole prime is equal to A prime plus B prime, right? These are two matrices, and if you add them together, take the transpose of the sum of them, then that is equal to the the transpose of each of them, then added together. So what that means is that now if I take A as, basically if I write this as A plus negative B whole transpose, then of course that's going to be equal to basically A transpose plus negative B whole transpose, based on this. And then I can write this as A transpose plus, basically take the negative sign out, write it as negative of B transpose, A plus negative of B transpose, and therefore I can write it as A transpose minus B transpose, which means that basically now what I want to show is that I want to show that A minus B whole transpose is equal to A transpose minus B transpose. Okay. So what I can do, which is, of course, this is not the best way to do it, but what I know is that A plus B whole transpose is equal to A transpose plus B transpose, right? So if I write, so of course I can write, instead of A plus B whole transpose, I can write A plus A minus negative B. Instead of this, I can write A minus negative B, because whole transpose, because when you subtract the negative of a matrix from another matrix, it's the same thing as adding those two matrices together, because I know that basically A minus B is the same thing as A plus negative B. That we already know, right? So A minus B is the same thing as A plus negative B. A plus negative B. So let me start with the right. So if I say that A plus negative B whole transpose is the same thing as A minus B whole transpose, and that is of course equal to A transpose plus negative B whole transpose, and that is equal to A transpose plus negative of B transpose, which is equal to A transpose minus B transpose. So that way you can prove it. It actually works out. I didn't know how to do it, but it seems that it works that way. So we know that from matrix addition, we know that basically A minus B is the same thing as you can use the rules of matrix. When you want to subtract, you can use the rules of matrix addition and add the negative of the second matrix to the first matrix, right? So based on that, I can say that A minus B is equal to A plus negative B. So A minus B is A plus A minus B is equal to A plus negative B. And if I take the transpose of both of them, that would be allowed, right? Now, this is in turn equal to, based on the fact that A plus B whole transpose is equal to A transpose plus B transpose. Instead of A plus negative B whole transpose, I can write A transpose plus negative B whole transpose, right? And then I can take the negative out because negative B whole transpose is the same thing as negative of B transpose, and well, and then that is the same thing as, of course I have to write parentheses here, and then that is the same thing as negative into positive is negative A transpose minus B transpose, right? So which means that basically, long story short, that means that A minus B whole transpose is equal to A transpose minus B transpose, which I can use here to write A transpose minus A transpose whole transpose. And therefore I can say that basically I can write this as A transpose minus A, because A transpose whole transpose is equal to A, right? Now, over here we said that C is equal to A minus A transpose, and this is A transpose minus A, so I can write it as negative of A minus A transpose, and that is equal to negative C. This basically means that C prime is equal to negative C, which means that basically C is a skew symmetric matrix, which means that A minus A prime is a skew symmetric matrix. So that proves that basically if you have, that proves basically we have proved these two, meaning that for any square matrix A with real number entries, A plus A prime is a symmetric matrix and A minus A prime is a skew symmetric matrix. Okay, so that was theorem number 1. Okay. So now we have another theorem here, and that is theorem number 2. Theorem number 2 is also kind of related to theorem number 1, meaning that in theorem number 1 we said that if you have a square matrix A with real number entries, then A plus A prime is a symmetric matrix, A minus A prime is a skew symmetric matrix. And we are going to use this here in theorem number 2 to prove that theorem 2, to prove that basically any square matrix any square matrix can be written as the sum of a symmetric and a skew symmetric matrix, as the sum of a symmetric and skew symmetric matrix. So what that means is that, well, it's pretty clear. If you have any square matrix, you can write it as the sum of a symmetric matrix and a square symmetric matrix. Now to prove this, you can say that let A, for example, let A be a square matrix. And now I can of course write A as one half of A plus A prime plus one half of A minus A prime, and I can write this because if you expand this, you will get 1/2 times A plus 1/2 times A prime plus 1/2 times A plus 1/2, actually minus 1/2 times A prime, and then these two will cancel out, and then 1/2 A plus 1/2 A is equal to A, which means that A is equal to A, right? So these two which means that your RHS is equal to your LHS. So since that is the case, of course I can write this expression or this equation. Now from theorem 1 we know that basically A plus A prime is a symmetric matrix, and A minus A prime is a skew symmetric matrix. We already proved that. And now, so what we have written here is basically we have 1/2 times basically A plus A prime, and basically A is now the sum of 1/2 of A plus A prime and 1/2 of A minus A prime, right? So we need to show that basically, well, of course, A plus A prime is a symmetric matrix, and A minus A prime is a skew symmetric matrix. We need to show that basically 1/2 of A plus A prime is also a symmetric matrix. And also we need to show that 1/2 of A minus A prime is also a skew symmetric matrix. Now the reason why I'm saying that we need to show these two is that basically if I can show that 1/2 of basically 1/2 times, for example, if I can show that 1/2 times A plus A prime is a symmetric matrix, and 1/2 of A minus A prime is a skew symmetric matrix, then over here I have written A as 1/2 of A plus A prime plus 1/2 of A minus A prime. So this would be a symmetric matrix. This would be a skew symmetric matrix, and therefore I would have shown that A could be written as the sum of a symmetric matrix and a skew symmetric matrix, right? Now, in order to do that, in order to show that, basically to show that basically 1/2 of A plus A prime is a symmetric matrix, is a symmetric matrix, we have, so now in order, basically in such situations, you cannot think in the air. I mean, you cannot think in different directions. You have to basically organize your thoughts so that you can see the solution. Otherwise, you wouldn't see the solution in a million years. There is a way to do this, and I will show you how you can do it. For example, in this, using this simple example, and then you can generalize this to other things that you do in mathematics. So basically, there are always things that you know about something that you want to prove. For example, what we know that basically, we know that A plus A prime, we know that A plus A prime is a symmetric matrix. Is a symmetric matrix, right? We already know this because based on the theorem 1, we know that A plus A prime is a symmetric matrix. Now, what that means in mathematical terms is that when based on the definition of a symmetric matrix, we said that if you have a square matrix A, then if A prime is equal to A, then that matrix is called a symmetric matrix, right? If I'm not mistaken, yes. So when I say that a matrix is a symmetric matrix, that means that the matrix the matrix itself is equal to the transpose of the matrix is basically equal to the transpose of the matrix. So that means that A plus A prime is actually equal to A plus A prime whole transpose, right? That's the meaning of this, the statement that I have written here. Now we want to show that these are very important. These steps are very important. Otherwise, you would end up confusing yourself. This is very, very, very absolutely important. You have to write it down, and once you write it down in this logical order, you will always get the solution. It's not complicated at all. But when you're thinking about the problem in your head, most often than not, 95% of the time, you will not get the solution. So we want to show that basically now 1/2 of A plus A prime is a symmetric matrix. Is a symmetric matrix. That is, we want to show that basically that is actually A prime, right? So we want to show that basically this matrix, which is 1/2 of A plus A prime, this matrix here, is actually equal to the transpose of itself, meaning that it's 1/2 of A plus A prime, 1/2 of A plus A prime whole prime, right? So you want to show this, and you can use all the information that you have. Now what you can do is that you can start from, for example, one side of this equation, and basically try to write any side that you choose. You try to write it in terms of, or try to write it exactly like the other side of the equation. If you can show that your, for example, LHS is equal to your RHS, or your RHS is equal to your LHS, that means that you have proved it, right? So I start from the left hand side, the LHS of, for example, call it 1. The LHS of 1 is basically 1/2 of A plus A prime. And also something that we know is that we have already proved that basically for any matrix, we have already proved that for any matrix A, for any matrix A, we proved that basically K times A whole prime is equal to K times A prime, meaning that if there is a scalar here that you have multiplied by a matrix, and if you take the transpose of the whole matrix, then you can take that K out, right? So I can write this as basically okay. So now basically the RHS is 1/2 of A plus A transpose whole transpose. That is the RHS. Based on this, I can take the 1/2 out. I can write it as 1/2 of A plus A transpose whole transpose, and we know that that's equal to basically, A plus B whole transpose is equal to A transpose plus B transpose, which means that would be 1/2 of basically A transpose plus A transpose whole transpose, and that's equal to 1/2 of basically A transpose plus, and we know that A transpose whole transpose is equal to A, so that's equal to A, which is equal to basically the RHS that we have, the LHS that we have here, right? So, and therefore you can say that basically 1/2 of A plus A prime, 1/2 of A plus A prime is a symmetric matrix. Is a symmetric matrix. Now what we need to show is that we need to show that also 1/2 of A minus A prime is a skew symmetric matrix. So we already showed this one. Now we need to show that 1/2 of A minus A prime is a skew symmetric matrix. Now in order to do that, I'm not sure if I'm going to miss anything here. No, I guess I'm going to be fine. Okay, so I need to show that A plus, so basically what we know, or the given over here is that A minus A prime is a skew symmetric matrix, right? Matrix. And what that means is that by definition, basically the skew symmetric means that the transpose of the matrix, what that means is that the transpose, that is basically the transpose of the matrix A minus A prime, a minus a prime whole prime is equal to negative of a minus a prime. That is the meaning of this statement, which is a minus a prime is a skew symmetric matrix. By definition, that means a minus a prime whole prime is equal to negative of a minus a prime. And we want to show that basically 1/2 of a minus a prime is a skew symmetric matrix, right? That is, we want to show that basically 1/2 of a minus a prime whole transpose is the same thing as negative of 1/2 of a minus a prime. We want to show this, right? Now what I can do here is that I can take that's basically what I want to prove. And so I start with for example, the LHS of 1, the LHS of 1, and so I have 1/2 of a minus a prime whole prime, and based on the fact that ka whole prime, what did I say over there? Ka whole prime is equal to k times a prime. Based on this, I can write this as I can take this 1/2 out and write it as 1/2 of a minus a prime whole prime. And then I can say that, so this is based on the fact that k times a whole prime is equal to k times a prime. This is because of this, right? And then I can write this as, and then we also proved before that a plus b whole prime is the same thing as a prime plus b prime, and we also showed that a minus b whole prime is the same thing as a prime minus b prime. We already did that. So I can write this as 1/2 of a prime minus a prime whole prime, right? And that is because a minus b whole prime is the same thing as a prime minus b prime. And now I can write this as basically 1/2 of a prime minus a, and that is because basically a prime whole prime is equal to a, right? And so that is the same thing as 1/2 of basically a prime minus a. I can write this as 1/2 times basically negative of a minus a prime, right? 1/2 of negative of a minus a prime, which is the same thing as negative 1/2 of a minus a prime, right? So that means that that is basically what I wanted to show here. That basically means that well, 1/2 of a minus a prime whole prime is equal to negative 1/2 of a minus a prime. And that means that basically a minus a prime, and that basically means that a minus a prime is or 1/2 of that actually, 1/2 of a minus a prime is a skew symmetric matrix, right? So now we have shown that and also we have also shown that basically 1/2 of a plus a prime is a symmetric matrix, So putting all of that together, we took A as a square matrix, and we wrote A as basically 1/2 of a plus a prime plus 1/2 of a minus a prime, right? And if you basically expand this, you will get the same thing as A. And since we have shown here that 1/2 of a plus a prime is a symmetric matrix and 1/2 of a minus a prime is a skew symmetric matrix, therefore any square matrix A, can be expressed as the sum of a symmetric and a skew symmetric matrix. Okay, now this was actually not that important. I mean, it doesn't really matter whether you prove this exactly that for example, but basically it's important that you're able to actually do this on your own, because once you can do this, then you know how to use logic in mathematics, and that's important. Then you can basically use it in different you'll be able to use it in different areas of mathematics. You'll be able to use it in different areas of, I don't know, other sciences and so on and so forth. And the only way that you can learn that is basically following the text that you have and understanding each and every step of the way. And of course you have to be able to produce it yourself as well. And over time, when you're doing geometry, when you're doing other things, you'll be able to use logical deduction and logical reasoning and so on and so forth in order to prove something, which is of course in many cases very important, because most of the time you think that something is true, but then when you try to prove it, sometimes you even notice that the opposite of what you thought was true is actually true. And sometimes you won't even be able to prove it, meaning that you thought that whatever it was that you thought was true, you actually don't know how you thought so, which means that your thoughts was based on absolutely nothing, which means that your thought was actually a baseless thought, right? So that's the importance of proving things, otherwise, and theorems and so on and so forth. Okay. Now, we have a couple of examples, only only a couple of them, only one, that we will do in the, we can actually do it in this video and then end this video here.